question is, do you remember the date, exact date when you last say I love you to your parents? You can't remember. It's not okay, because we should love our parents. We should love and respect our parents. We should say I love you to our parents as much as possible. What they want from us? Our parents want good results, and they want my son or daughter will be a good human being. That's why you study, you go to a school or college and try to make yourself a good man. What do you think? Do you find anyone who loves, who can love more than your parents? You can't find anyone in this whole world who loves more than your parents. So, my dear students, give me a promise. You all try to say I love you to your parents at least once a day. It will increase the relationship between you and your parents. So, my dear students, today, as you know before, our topic is valence shell electron pair repulsion theory. Why we learn this theory? To determine the geometrical shape of polyatomic molecules like barium chloride, carbon dioxide, methane, ammonia, water. We should learn this valence shell electron pair repulsion theory. My dear students, you know the shape of water is V. The shape of ammonia is trigonal. The shape of barium chloride is linear. The shape of carbon dioxide is also linear, and the shape of methane is tetrahedral. My question is, why the shape of water is V, the shape of ammonia is trigonal, barium chloride is linear, carbon dioxide is also linear, and methane is tetrahedral? By knowing this valence shell electron pair repulsion theory, we can understand why the structure of these polyatomic molecules are this. So this is our today's topic. So, my dear students, let's start. Let's discuss our topic in details. Before entering details, we should learn some special points. And this bond is called sigma bond. Sigma bond pair. Sigma BP. BP means bond pair. BP means bond pair. Bond pair, and we know single bonds are called sigma, and one bond has 2 electrons, so we can call it sigma bond pair, and these 2 electrons are called lone pair. Here 2 lone pair is present in water molecule, lone pair, and barium has no lone pair, carbon has no lone pair. Here this bond is called sigma bond pair, and another double bond is called pi bond pair. Here this is called sigma bond pair, and this is pi bond pair, and all are sigma bond pair. You know, the central atom is surrounded by electrons, and these electrons are 3 types. Number 1 is bond pair electrons. That means bond pair electrons are 2 types: sigma bond pair and pi bond pair, and lone pair electrons. Lone pair electrons. So, my dear students, here central atom carbon has 4 outermost shell electron, that means valence shell electrons, and it forms 4 single bond. So carbon gain 4 electrons here from these 4 bond. That means total electron will be 8, and this is 4 pair. 8 electrons can form 4 electron pair. This 4 comes from valence shell electron of carbon, and for one bond another 1 electron gain carbon. So carbon form 4 bonds, so we add 4 to this 4, and total number of electron is 8. 8 means 4 pair. This 4 pair has 2 types, 2 sigma bond pair and 2 pi bond pair. So my dear students, that's how we can calculate the electron pair and type of electron pair. Now, what is the relation between these sigma and pi bond pair electrons to the geometry of the molecule? We should learn this. For example, for carbon dioxide, so we get 2 types of bond pair electrons: sigma bond pair and lone pair and pi bond pair electrons. These electron pair repulse each other and form a special geometrical shape, and that geometrical shape denote the geometry of that component. So this electron pair has influence on the geometry of that component. Now we should know pi bond pair electrons has no contribution to the geometry or shape of a polyatomic molecule. Only sigma bond pair and lone pair electrons has contribution to the geometry. So my dear students, these 2 pi bond pair electron has no contribution to the geometry. So we should consider only these 2 sigma bond pair electrons. Now we have to learn what is the relationship between sigma bond pair and lone pair electrons to the geometry of the compound. So we should learn a chart. Here number of sigma bond pair and lone pair, and here the shape or special arrangement, shape or geometrical shape or special arrangement of electron pair surrounding the central atom, and here we learn the bond angle. If the number of bond pair and lone pair electrons, total number of bond pair and lone pair electrons will be 2, the shape will be, this is central atom and this is adjacent atoms, that means linear, and the bond angle is 180 degree. In case of carbon dioxide, carbon has 4 valence electron, and we know carbon form 4 sigma bond, 4 bond, 2 sigma bond pair and 2 pi bond pair. So total number is 8. 4 from valence electron and 4 from 4 electron gained from 2 oxygen atom. So 8, that means 4 pair. Here 2 are sigma bond pair and 2 are pi bond pair. So we should consider only sigma bond pair. That's why the geometry of carbon dioxide will be linear. That means this is the geometrical shape of carbon dioxide and the bond angle is 180. Another example, BeCl2. BeCl2. Here the central atom is barium. How will we find the central atom? The atom which presents smaller amount, lesser amount, is called central atom. The barium central atom here, barium has 4 valence electron and 2 chlorine atom attached. So barium has 2 valence electron and 2 electron gained from 2 chlorine adjacent chlorine. So total number of electron 4. That means 2 pair. And all are sigma bond pair. So the geometry of barium chloride will be linear, geometrical shape, and the bonding will be 180. Central atom barium to adjacent chlorine attached in this geometrical shape. So, my dear students, we know the geometrical shape of carbon dioxide and barium chloride from valence electron pair repulsion theory. Now, if the number of bond pair and lone pair electrons is 3, the special arrangement shape or geometrical structure will be trigonal. And the bonding is 120 degree. And the example is BF3. Here the central atom is boron. The valence electron of boron is boron 5 2 3, and 3 electrons gained from 3 fluorine atom. So total 6 electrons, and 6 electron means 3 pair. And all are sigma bond pair. No lone pair electron present in this compound. So 3 pair means trigonal. The geometrical shape will be trigonal. So we can represent BF3 as BF3. Bond angle will be 120 degree, and the geometrical shape is trigonal. Now, if the number of bond pair and lone pair electrons is 4, the shape will be central atom tetrahedral. The bonding angle will be 109.5 degree. For example, in case of methane, the central atom is carbon. Carbon has 4 valence electron and 4 electrons gained from 4 hydrogen, adjacent hydrogen. So total electron is 8 is equal to 4 pair. Here all are sigma bond pair. So the geometrical shape of methane is tetrahedral, and the bond angle is 109.5. So, my dear students, in this way we can easily determine the geometrical shape of this type of compounds. Now, if any lone pair electrons are present, the shape of this compound will be changed, will be distorted, because lone pair and lone pair electrons repulse to each other. bond pair repulsion is less than lone pair, and bond pair electron repulsion is more less than lone pair electrons. So with the increase of lone pair electrons in a compound, the distortion of bond angle will be also increased. So the geometrical shape will be changed. If no lone pair electrons, there are no lone pair electrons present, then the geometrical shape will be tetrahedral for 4 sigma bond pair lone pair electrons. But for 4 sigma bond pair lone pair electrons, if there is any lone pair electrons are present, the geometrical shape will be distorted. Let us see an example. In case of ammonia, the central atom is nitrogen, so the valence shell of nitrogen is 5 and 3 electron gains from 3 hydrogen, so total 8 electrons, that means 4 pair, but only 3 hydrogen are present. So 4 pair has 2 types. One is bond pair, and bond pair electrons is 3 hydrogen atom attached to nitrogen form 3 bond pair, but another bond is absent. This bond is called lone pair electron. So in ammonia, 1 lone pair electrons is present. So the structure of ammonia will be like that, and these lone pair electrons repulse each other, and lone pair bond pair electrons also repulse each other. For this repulsive force, the bond angle will be closer. The bond will be closer to each other, and the bond angle will be 107 degree. Here, in case of methane, also 4 bond pair and lone pair electrons are present. No lone pair, all are bond pair. But when 1 lone pair electron and 3 bond pair electrons are present, the bond angle will be distorted like that. If more lone pair electrons are present, bond angle will be distorted more. For example, in case of water, oxygen is the central atom, and the valence shell of oxygen is 6, and 2 electrons gained from 2 hydrogen atom. So here 8 electron means 4 pair. 2 hydrogen is present, so the sigma bond pair will be 2 and lone pair will be 2. So what happened now? Here 2 lone pair electrons are present and 2 bond pair electrons are present. So bond angle will be distorted more, and the bond angle will be 104.5 degree. So my dear students, in this way we can determine the exact geometrical shape of a polyatomic molecule by applying valence shell electron pair repulsion theory. Now if the bond pair and lone pair electrons are 5, the geometrical shape will be like trigonal, planar, trigonal, bipyramidal. This is a trigonal, and this is a plane, and these bonds are perpendicular to this plane. So the bond angle will be 90 degree, and all these bonds are 120 degree. So here bond angle will be 120 and 90 degree. 120 degree and 90 degree. For 6, the geometrical shape will be octahedral. This is a plane, and these bonds are 90 degree, and all these bonds are also 90 degree. So here the bond angle will be 90 degree. These bonds are perpendicular to this plane, so the bond angle will be 90 degree. Or if we divide 360 degree by 4, we get 90 degree. So all bonds are 90 degree in octahedral. This is trigonal bipyramidal. Trigonal bipyramidal. And this is octahedral. So, my dear students, in this way we can easily find the geometrical shape of a polyatomic molecule by applying VSEPRT theory. Now we want to study some special cases, some application of this valence shell electron pair repulsion theory. By knowing these special cases, we can solve some special problems. For example, why the bond angle of NH3 and NF3 are different? Why the bond angle? We want to solve a critical problem. Our problem is why the bond angle of NH3 is higher than NF3. So, at first we want to calculate the electron pair surrounded by central atom. Nitrogen has 5 valence shell electron and 3 electron comes from 3 adjacent nitrogen. So 8 electrons means 4 pair. On the other hand, in case of NF3, nitrogen has 5 electrons and 3 electrons comes from 3 fluorine atom. So 8, that means 4 pair. Here 3 are sigma bond pair and 1 is lone pair. Here 3 sigma bond pair and 1 lone pair. So same resultant, 3 sigma bond pair, 3 sigma bond pair, 1 lone pair, 1 lone pair. But the bond angle of these two compounds are not same. Why? That is our question. Fluorine, 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 hydrogen, hydrogen, hydrogen. This is because between fluorine and hydrogen, the electronegativity of fluorine is higher than hydrogen and nitrogen. Fluorine is higher electronegativity than nitrogen also. So this between nitrogen and hydrogen, electronegativity of nitrogen is more, and between fluorine and hydrogen, electronegativity of fluorine is more. So these bond pair electrons comes closer to fluorine atoms, and in case of ammonia, the bond pair electrons have come closer to nitrogen atom. Due to the increase of electron density in nitrogen atom, the repulsive force is also increases. So the bond angle of ammonia is we know 107, but in case of NH3, the electron density lesser in nitrogen atom because these bond electrons come closer to this fluorine atom. So the bond angle of NF3 is more than NH3, and the exact bond angle is 102 degree. Due to the repulsive force present in ammonia, due to the increase of electron density at nitrogen atom, the bond angle is more. But here, no repulsive force is present, so the bond angle is less. Okay, my dear students, in this way we can answer this type of question. Let us see another point. Single bond, double bond and triple bond. Here one sigma bond pair, here one sigma bond pair, one pi bond pair, here one sigma bond pair and two pi bond pair. So with the increase of pi bonds, repulsive force also increases. With the increase of pi bond, here when triple bond there are two pi bonds, when double bond there are one pi bond, and sigma bond has no pi bond. So with the increase of pi electrons, number 2 point, the repulsive force is also increases. For example, phosgene gas, if you consider phosgene gas COCl2, what happened? C double bond O and Cl2. Now the bond angle should be 120 degree, but due to the presence of pi electron, this repulsive force of these bonds are increased. That's why this bond angle is more than 120. It will be 124.3 degree, and these bonds comes closer to each other, and exact bond angle is 114.3 degree, because these come closer. These bonds are come closer to each other due to the repulsive force of this pi electron. So when no pi bonds are present, the bond angle will be 120, and due to the presence of this pi bond, the repulsive force increase and the bond angle is also increased, and this bond angle is decreased. That's why in phosgene the bond angle will be 1.4 and 1 to 4.3. Let us see another question. Why the bond angle of phosphine and ammonia are different? This is our third question, and the exact bond angle is 93.4 and here 1070. So why the bond angle of ammonia is higher than bond angle of phosphine? Here both has 3 sigma bond pair and 1 pi bond pair. So total 4 electron pair surrounded by central atom, and both has 3 sigma bond pair and 1 pi bond pair. So the bond angle should be same, but bond angle is different. This is because P has vacant d orbital. So with the increase of vacant d orbital, the repulsive force is also increased. Due to the increase of this repulsive force between lone pair and bond pair electrons and lone pair and lone pair electrons, the bond angle will be distorted more. Nitrogen has no vacant d orbital, so here the lesser repulsive force will be occurred. But in case of phosphine, the repulsive force will be more than ammonia. So the bond angle of ammonia is higher than phosphine. In this way, we can describe why the bond angle of water and H2S are different, and why bond angle of water is more than bond angle of H2S. And the exact value is 104.5, and in case of H2S, the bond angle will be 92.1 degree. Here the same explanation, nitrogen has no vacant d orbital but sulfur has vacant d orbital, so the bond angle will be distorted more in case of H2S, so the bond angle is higher, the bond angle of water is higher than H2S. Both has same number of sigma bond pair and pi sigma bond pair and lone pair electrons, but bond angle are different. So we face this type of question in our exam, and we can answer this type of question by this way. So my dear students, practice at home so that you can do well in the exam. So I want to give you some homework. Why the structure, why the geometrical shape of these molecules are different. Determine the geometrical shape of the following compounds. Determine the geometrical shape of the following compounds. Of the following: carbon dioxide, ammonia, PCl3, PCl5, XeF2, SF2, SF4, SF6, IF7, etc. So, my dear students, today we learned a lot of things like modal education, then how can we determine the geometrical shape of polyatomic molecules by using